Okay, hi, hello. My name is Elisa, but you can call me Ellie.
Hello, my name is Jonathan. Uh, yeah, short for
and
Jonathan.
yeah, and we'd like to present our final project entitled "Predicting Connecticut River Discharge: A Bayesian Approach." Um, I'd like to give a little bit of a background, starting from pretty much the global view all the way down to our project. And it starts with the importance of a hydrograph. A hydrograph, it measures basically the flow of the river, which we call discharge. And we can not only infer discharge based on the shapes and the frequency, the steepness of these peaks, but also the size of the basin, seasonality, dominant water source, watershed history, soil properties, and maybe the gradient of the watershed, just to name a few. But the idea here is that for a hydrologist, a hydrograph is one of their main tools in the toolbox. So how do we compute discharge? And it's a very simple equation. Discharge we call Q is equal to the width times the depth times the velocity of a river and at a cross section. And these physical properties follow a statistical power law relationship. So you can choose either width, either height, or either velocity mapped over a certain amount of time, and you can infer discharge. So the graph on the right is an example of that power law relationship created in 1953. So these gauges are really, really useful, but it turns out most of them, they need quite a bit of infrastructure, time and money, quite a huge investment to maintain and rigorously calibrate. And so we have the USGS, United States Geological Survey, funded by the US government, that does a lot of that for us in the United States. And then you can see that it's around the rest of the world. Certain countries have devoted time and money into this, and certain countries haven't. So we don't have a really good idea worldwide what's going on in terms of discharge around the world. So in the field, you can use these gauges that we mentioned. We have a photo here on the left. Usually we use gauge height as a way to infer discharge. But now in the satellite age, we're actually about to be able to leverage remote sensing applications to help compute river discharge. This on the right is a photo of the Surface Water Ocean Topography, or SWOT satellite, that our lab is going to help calibrate, validate, help launch in the next year. And it's a radar satellite, and then what it will do is be able to measure water surface elevation. And from there, we're computing an algorithm to help from water surface elevation get ourselves to discharge large rivers about 90, 100 meters plus all over the world. So to validate SWOT, like I mentioned, there's a river discharge measurements. We would like to also use a Bayesian approach. And with this way, we can kind of use SWOT-like measurements or field measurements that we've already taken to simulate the satellite, plug them into our model, and see if we get an accurate discharge estimate. So we're going to use the Connecticut River, one, because it's in our backyard, and two, because it's also one of the SWOT calibration validation sites. And so once it launches, it's going to the pseudo orbit and we'll be in the field measuring the water surface elevation and the discharge for this river next year. Our methods overall include a ordinary least squares linear model to a frequentist approach. We then move to a Bayesian linear model as a Bayesian approach, and while it gets a lot of what we're looking for in terms of looking at different variables by time and by width, by height, for example, it's really difficult to also think about location site, because these different gauges that we measure will depend on where they are, and the discharge will depend on where they are, and that's a really important aspect of building a well-fitted model. So in the end, we present a Bayesian hierarchical model. Linear models. This here is a presentation of our first linear model. This is a non-Bayesian approach. We found that by transforming the discharge. So we have log discharge, we can find, and then testing for heteroscedasticity and for our equal assumption of variance, we have a pretty good fit. There are no variables that lie outside of Cook's distance, which means that we have no outliers that are overall skewing this data.
So for the Bayesian regression model, we also did the same thing like in the ordinary least squared method. Like we fit first for the regression coefficient and used it and plug it into our regression Bayesian regression model. So here are our priors. Like we use the weakly informative priors for our model, and we have this model likelihood, and we included here what's also included in the ordinary least square regression model that we have. So our parameters, our variables include the model, the month from month 1 to month 12, and we also have the variable for year, and the width variable and the height variable, and get it their corresponding coefficient based on Bayesian regression approach. So here is a snapshot of our algorithm that we used for obtaining the posterior betas for our model. So we first plug in our priors, which are included here. Well, like we have the prior variance setup, and then the prior sample size, and the G prior. So we intentionally make the G prior bigger, and the prior variance and sample variance, sample size smaller, just to make our priors uninformative. And then before we can update our betas with a multivariate normal distribution, and then update it with sigma squared from our inverse gamma distribution, and then keep all the calculated values for the posterior of betas and sigmas at the end. So likewise, but in a different approach, we also used Bayesian hierarchical model. So here our priors include weakly informative, it should be informative, weakly informative priors. So we include a prior variant within group of our gauging station, and then the prior for sample size, and included here is also the degrees of freedom that we have to set up for our Markov chain Monte Carlo algorithm. So for our likelihood, so it's worth noting here that our variables reduces to only 4 instead of like how many before?
15.
15 before, because we just make the math variable a single variable here, and then capture the coefficient on our Monte Carlo algorithm. So for our hierarchical algorithm, it includes the flow that updates the beta based on the priors and the variables that we plug into the model. And then after getting the betas within the stations, we just update the data for the model with a multivariate normal distribution, and then update sigma, like the flow that we have in the previous Bayesian regression approach. And then from that sigma, we update S squared with the variance with our inverse gamma distribution based on our prior information, and then store also the posterior betas and sigmas, and the distribution from those hierarchical model. So for the data, also we prepared it by splitting the entire data set into two, with the training data set and then the validation data set. So we have 80% 80% for training data and then 20% for validation data. And then in the model performance assessment, we did calculated the mean absolute error and the Nash-Sutcliffe efficiency. So the mean absolute error is chosen so that we can also get or assess how our errors spread out to the model prediction, and the Nash-Sutcliffe efficiencies for the deviation of the prediction based on the field measurement that we have from the river gauge discharge.
So a little bit about our results. What did we find? So by comparing the coefficients, the beta or the ordinary least squares coefficient between our two linear models, we find that they're essentially identical, showing that the Bayesian model and the frequentist approach have created essentially the same fit. And that translates here into our actual predicted versus observed data. And so you see on the x-axis we have the observed. Again, this is a log transformed discharge. And then on the y-axis we have what the model predicted as our discharge, and you can see a pretty good fit on both of them, and the same fit on both of them, and it tends at the very highest discharge to just over predict just a little bit, and then the very lowest discharge to also under predict just slightly.
So here in the Bayesian hierarchical model, we also see a similar trend like the previous slide, that there are some under and over prediction from the data points that we have. What we're seeing here is the same scale that we previously showed. It is a log transformed discharge values from our model and from the field measurement that we used in the model. So here on the left panel, we just demonstrate how the hierarchical model behaves in comparison to the ordinary least squared regression. So for the ordinary OLS regression, we can see that here the regression lines from the station-specific regression lines are varying, and there are some regression lines that are extremely steep in slope. So these are the stations that are having higher coefficient in their betas. And then here in the Bayesian hierarchical regression, we can see that through the use of thetas or the within groups betas, we can see that the station-specific regression lines shrinks, and it helps because the within groups regression line shares information among the stations and in the locations of the gauging stations that we have. So we can see that the mean regression line here, or the solid line here, goes down in the slope or the steepness in comparison to the OLS regression. And so here we have the model performance. So that we can evaluate how our models, 3 models that we assessed performs in terms of predicting the actual values of the discharge that we really want out of this project, and then assess how the prediction deviates from the field measurements or the actual field measurements conducted by collected by our USGS. So here in the ordinary least squared and then in the Bayesian regression, they are almost the same, since in the previous slides that we showed on the results, they are showing almost comparable coefficients and the parameters that we obtained from OLS and from the posterior distributions. So as expected, you can see that they are almost the same, and even in the NSC, they are actually identical. And in comparison here to the Bayesian hierarchical, we obtained a really high error. So really high mean absolute error, like it is nine times higher than the errors that we obtained from the previous 2 models. So we just like to stress here that in the Bayesian hierarchical, it's pretty different in the model development, because the parameters or the variables that we use there for the month is only a single one, instead of separating the variables into 12 months as factors.
So in summary, we were able to overall accurately predict river discharge for the large majority of our data, and that Bayesian methods are very well suited for this type of application. But it does have a better fit for the medium low discharges, and it has a worse fit, tends to overpredict the extremes, the lower and the higher discharge. So if we were to continue on this project in the next few weeks, we would fine tune the hierarchical model to be able to produce the monthly coefficients, and thus likely probably increase its accuracy. And then if we were especially interested or creating studies that looked at the sites with the lower discharge or especially higher discharges, likely maybe in springtime, which is another reason why those monthly estimates are so important, we might be able to create sort of specific priors that target and are better and create a better fit for those situations. So yeah, that's in summary all of our final Bayesian project. And yeah, we'd like to thank Dr. John Stoudemire for his guidance or his help in creating this model. And yeah, I would like to thank you for watching.
Thank you.